So let's try some IB questions for optimization. So here we have a question number 1 from 2016 November, paper 2, means we can use GDC. So we have a water container that is made with the shape of cylinder with the internal height h and internal base radius r centimeter, and the graphs of the f and g intersect at x equals p and x equals q, where p value is less than q value. So the water container has no top, and the inner surface of the container are to be coated with a water-resistant material. So the volume of the water container is 0.5 centimeter cube, and the water container is designed so that the area to be coated is minimized, and 1 can of water-resistant material costs a surface area of 2000 centimeter cube. So this is all the information that we need to know. So question A, we need to write down a formula for A, the surface area to be coated. So there's only one bottom that we need to consider. So surface area equals pi r squared plus the area of the curved surface of the cylinder has the formula of the 2 pi rh. So we can calculate the surface area of this can using A equals pi r squared plus 2 pi rh. And all these formulas are actually in your formula booklet, so you can always look it up. And question B, we need to express this volume in centimeter cube. So we know that the volume of the can is 0.5 meter cube. So we need to convert 0.5 meter cube to centimeter cube by using conversion factor. So every 1 meter is 100 centimeter. So we just have to do cube so we can get rid of all the units. Then we get this value as our volume in centimeter. And question C, we need to write down in terms of R and H the equation for the volume of this water container. So volume of any container is base times height. So our base is a circle, so it is a pi r squared, and the height h, and it is equal to the value that we just converted. So question D, we need to show that the A is equal to this. Okay, so it seems like we have to use both surface area formula. A equals 2 pi rh plus pi r squared, and have to do something with the volume so we can get rid of this extra h, right? So pi r squared h is equal to this value. Then we can say that let's use this. So pi rh, we have pi rh in the surface area formula, and we have pi rh, pi r squared h in the volume formula. So it means we can rearrange this volume equation as pi rh, and we are moving r to the other side, one of the r to the other side. So we get this. Then we can substitute this part with this new equation. Okay. Then we can have A equals 2 times over r plus pi r squared. Then we have shown that it is also equals to this value. Okay. Then question E, we need to find the dA over dr. That means we need to differentiate this. So question E, we need to differentiate the surface area function in terms of dr. So we already know that surface area is actually equals to pi r squared plus over r, and this is equal to pi r squared plus r to power of -1. So when we differentiate this equation, it becomes dA over dr is becoming 2 pi r plus -1 times -2. So this is same as 2 pi r minus negative 2, right? Or we can also write it as 2 pi r minus over, don't forget the r squared. Okay, then question F, we need to find the r value that minimizes the a. So we are doing F now. So it means we need to find the minimum point or the turning point. That means we can set 2 pi r minus over r2 equal to 0 and solve for the r value, which is same as I can move r squared to the other side, and this becomes r cubed equals over 2 pi. Then r value is same as cube root 2 pi. So r value is approximately 54.19. Okay. Then question G, we need to find the value of the minimum area. So now since we know that r value is 54.19, to find the minimum area, we can substitute 54.19 into the area formula. So we do A equals pi times 54.19 squared plus over this. Then we get approximately this value, square, don't forget the square, square. Then question H, it says that we need to find the least number of the cans of the water resistant material that will coat the area in part G. So each can of the water resistant material coats about 2,000, right? This is per can. Then to find the least number of the cans needed, we need to divide the total area by the area each can serve. So we get 13.84, and since we cannot have a fraction of a can, we should need at least 14 cans of the water resistant material. And that's the end of the question. So you can see that this question is actually a combination of the geometry and calculation. So if you have IB questions on optimization, it will probably combine with the geometry.